Hello, everyone, and welcome to our webinar for today. I am your host, Scott Hartsaw, and today's presentation is a good one that's entitled In-Situ Chemical Reduction and Enhanced Bioremediation to Treat a Co-Mingled TCE and Hexavalent Chrome Plume. I want to mention that this webinar has been approved for CEU PDH credit, and I will put the sign-in sheet onto the chat feature here within Teams, and you can download that there. If you have any trouble getting the Teams version to download for you, you can always send me an email, and I'll get that back to you so that you can fill that out and return it, and we'll get your certificate processed. See, next slide. A few housekeeping items. We will try to keep everybody muted as they call in so that we give everybody the opportunity to hear what's being presented. You can submit questions using the chat feature, or you can hold questions to the end. We will be saving 10 or 15 minutes at the end of the presentation for a Q&A session, and we will address questions at that point. And we would ask that you would state your name at that point in case we need to follow up and get you answers to any questions that we can't cover during the presentation here. Next slide. Our agenda briefly will give you an introduction into the speakers who will be presenting today. They will give a core value moment, as we like to do at the beginning of these presentations, and then the presentation and the Q&A session at the end. Our presenters today, Dr. Jim Liu is a Parsons Fellow. He brings a PhD in environmental engineering and over 30 years of experience in designing, managing, directing, and executing these kinds of projects, doing groundwater investigation and remediation. And Christy Diller will be presenting with him. She brings 13 years of experience in environmental investigations and remediation, and specializes in situ groundwater remediation, pretty similar to what you're about to see. So with that, I'm going to turn it over to Christy for the core value moment. Christy.
Thanks, Scott. Hey, everyone. Thanks for joining us today. We begin each of these presentations with a core value moment. Parsons' 6 core values are shown on this slide. I'm going to focus in on a safety topic today. Parsons is firmly committed to maintaining a safe and healthy environment in all our offices and on each of our products. But the topic I'm going to cover today applies to more than just Parsons employees. It's applicable to everyone. We're just now entering what are typically the most vulnerable months for wildfires, September and October. But the number, severity, and overall size of wildfires and the typical wildfire season is increasing. Wildfires, of course, are especially impactful and devastating if they happen in your community, but wildfire smoke can impact air quality up to thousands of miles away. Those of us who live in the West have become accustomed to living with wildfire smoke. You know, here in the Denver area today, it is poor air quality because of the wildfire smoke from California. But I also know that this year fires in Canada, Minnesota, and the large fires in the West have affected air quality even all the way to the East Coast. This image is from a great online resource called fire.airnow.gov. It's a collaborative effort between the U.S. Forest Service Interagency Wildland Fire Air Quality Response Program and the U.S. Environmental Protection Agency. The map displays information from ground level air quality monitors, recording fine particulates from smoke and other sources. And the website also has information on the fires, smoke plume locations, and special statements and forecasts for each wildfire smoke plume. So how do we know if we'll be impacted by poor air quality? First thing, check your local air quality reports, such as those on fire.airnow.gov. It's especially important for you to pay attention to air quality reports if you are in a sensitive group, such as a person with heart or lung disease, an older adult, a person with diabetes, if you're pregnant, or if you're caring for children, including teenagers. Anyone can experience burning eyes, a runny nose, cough, wheezing, difficulty breathing in response to poor air quality and wildfire smoke. But symptoms may be even more severe in these sensitive groups. So then what can you do to protect yourself or your family when air quality is unhealthy? First, limit your outdoor activities during those periods. Second, keep your indoor air as clean as possible. You can use a portable air cleaner or use a high efficiency particulate air filter with your air conditioning unit to filter out particulates from indoor air. Finally, if you can't remove yourself from the poor air quality, like if you have to be doing field work with thick wildfire smoke in the air, the final option is to wear a mask. But don't rely on dust masks or bandanas for protection from smoke. If you must be out in smoking conditions, an N95 or P100 respirator capable of filtering small particulates can protect you, as long as it fits snugly to your face and is worn properly. The fire.airnow.gov website has more information if you'd like to look into this topic further. And now I'll pass it off to Jim to begin our presentation.
Thanks, Christy. First, I'm going to give a brief introduction of the background. Next slide, please. The site condition. We have two project sites. These project sites are separated by the road, the horizontal road, as you can see from the photos. The site number 1 is on the north side of the road, and the site number 1 was a formal chromium plating site. And of course, the plume from site 1 is chrome 6. And site number 2 is on the south side of the road. And it was a site of various industrial uses, like machine shop, aircraft manufacturing, and the plume is a TCE. And the commingled plume is where the red circle is. It's on the roadside area. So that's our commingled plume area. So for both sides, the soil types are sand and sandy silt. The groundwater is pretty deep, about 155 feet below ground surface. And groundwater generally flow to the north, but there is the groundwater depression is very close to the red circle area. That means the commingled plume area. For the commingled plume, the highest TCE we detect is 1.4 milligram per liter, and chrome 6 is up to 250 milligram per liter. Next slide, please. So this, if we look at the figures, this is the ISO concentration for TCE and the chrome 6 back to year 2013. The blue line are the TCE ISO concentrations. As we can see, the highest concentration, the ISO line is 1 milligram per liter. And the green lines are for the chrome 6. As we can see, the highest ISO concentration is 100 milligram per liter. So with such high chromium 6 concentrations, there's a challenge that we know high concentration always will inhibit the bacteria to biodegrade TCE. And from our previous testing by previous contractors, if the chrome 6 concentration can be reduced to below 5 milligram per liter, it will be easy for bacteria to biodegrade TCE. So with that in mind, we will need to find a remedy that can quickly knock down the chrome 6 concentrations and also maintain the anaerobic environmental conditions for TCE to biodegrade. So it looks like the ISCR, In-Situ chemical reduction, is a good option. So usually the chemical reagent that we used for ISCRs like ZVI, zero valent ions, or CPS, calcium polysulfide. Next slide, please. So for this remedial approach, the approved is we included two parts. The first part, we need to use the ISCR, In-Situ chemical reduction with calcium polysulfide, CPS, to reduce chrome 6 concentration to below 5 milligram per liter. And the focus on this part will be focused on the elimination or reduction of these unacceptable secondary impacts like the precipitation, hydrogen sulfide, to injection operations or soil permeability and groundwater geochemistry. So after we reduce the Chrome-6 concentration to below 5 milligram per liter, then we can apply the combined ISCR and EAB enhanced anaerobic bioaugmentation to degrade TCE to background concentrations, both biotically and biotically. So by using this combined methods, we create a strong reducing concentrations that can maintain a low Chrome-6 concentration and also allow the TCE to biodegrade. And the ISCR we used is the ferrous lactate. And ferrous lactate can transform TCE to acetylene abiotically. And the EAB we use are the mixture of substrate, like the EVO, emulsified vegetable oil. They are the food for the bacteria, pH buffers, so that can maintain the neutral pH for bacteria to biodegrade. And also some bioaugmentation cultures, and that's a special species of bacteria that can biodegrade the TCE to ethylene So for this presentation, I'm going to focus on the first part using CPS to reduce Chrome-6 concentration, and Christy will be focused on the second part, the combined ISCR and EAB to biodegrade the TCE. Next slide, please. Okay, start from here, I'm going to talk about how we are going to apply the CPS to reduce Chrome-6 concentration. Next slide, please. So first, we need to decide where we're going to put these injection wells. As I mentioned before, we need to reduce the Chrome-6 concentration to below 5 milligram per liter. So first, we look at this 5 milligram per liter ISO concentration, which is shown on the green line. So we need to put the wells within this green line area. And another factor we need to consider is the groundwater depression. That is, I put it on the groundwater elevation 19 feet, this blue line area. That means the groundwater will flow into this area. So we need to put our wells within the intersection of this blue line and also the green line. So we pick these three circles. These three circles are radius influence of 25 feet. And the center of these circles are the well locations. As you can see, these wells are very close to the high concentration, which is the 100 milligram per liter ISO concentration. Next slide, please. So if you have experience injecting a CPS, you will find that precipitation is a big issue. The issue from this precipitation, first, it will clog our injection above ground equipment like tanks, pipes, meters, etc. And these solutions will be difficult to operate. It will increase the injection pressure or decrease the injection flow rate. And when we inject into the wells, it will clog injection well screen. And after we inject into aquifer, it will decrease aquifer permeability and also decrease the injection rate of influence. That's all the issues associated with the precipitation. Next slide, please. Okay, these are the precipitations we usually observe from a typical CPS injection. If you look at the photos on the left-hand side, the four small photos, we see these precipitations on the hose end, flow meter, turbine, and so some drill. And if you look at the right-hand side, for the filtration, you can see all this precipitation accumulated on the inside of the filter bag, as shown on the bottom right of the photos. Next slide, please. So first, we need to think about what caused this precipitation, make this unstable. And we find the main factor is the pH. So if we look at the chemical equations on the bottom of the slides, there are two chemical reactions. The first one is the calcium polysulfide dissolved into the water, and we put CaS to simplify calcium polysulfide. Actually, the calcium polysulfide should be CaSX, but we make it easy, just we use CaS. Plus water, we generate this CaSHOH, and when this stuff further dissolve into water, as we look into the second chemical reaction, it will generate calcium hydroxide and hydrogen sulfide. So calcium hydroxide is how we have this precipitation, and hydrogen sulfide is usually health and safety issues. So if we can prevent the second chemical reactions, then we can reduce or eliminate the precipitation and also hydrogen sulfide. So if we go back to the equation number 1, the first equation, we look at the right-hand side, this CaSHOH, we have this OH. So actually chemical reaction is kind of equilibrium, it's a flow both directions. So if we increase the OH, so we will push the reaction back to a CaS plus H2O, so we can prevent the second equation to happen to generate precipitation and also hydrogen sulfide. So we come up with the conclusion that pH is the main control factor for CPS solutions. And if we have higher pH, we have more stable CPS solutions. So usually when we purchase the CPS solution, the commercial size is always 29%. And usually we have to reduce or dilute the concentration to the concentration we want, then we start the injection. But the moment we dilute the CPS concentration, we also lower the pH. So that's how the precipitation comes out. Next slide, please. So after we find the pH is the major factor to control the stability of the CPS, we think we can first do a bench test, see what kind of pH is required for the CPS solution for the site. For example, for this site, we need 5% CPS. And of course, the second objective is to find how much of the alkaline, like sodium hydroxide, we need in order to maintain high pH of the 5% CPS, that no precipitation. And you may ask why is 5%? Yeah, of course, yeah, this is site specific. Yeah, maybe different site has different concentrations. And for our site, this is decided by the first the CPS dosage requirement. If we know the CPS dosage requirement, then we will know amount of CPS we need. And this is also decided by the ROI. If we know ROI, then we will know what's the volume of CPS we need to inject. So if we know the amount of CPS and we know the volume of CPS, then we can come up with the concentration of CPS. So that's the 5% for the site. And for this approach, we make two 5% CPS. One is just potable water. The other one, we use high pH adjust 5% CPS. So we compare these two, we observed and do some testings. I will show the details on the next slides. As we can see from the photos, the left-hand side is the potable water 5%. As we can see, the jar looks cloudy, murky, because we have this precipitation adhere to the jar surface. And if you look at the left-hand side, yeah, that is the pH adjusted 5% CPS solution. It's pretty clear. Looks like the jar is clear. So our results is if we, for this 5% potable water, we will generate coarse and settled particles. But if we adjust the pH high, then we'll have fine and suspended particles. So our conclusion is for 5% CPS solutions, if we can maintain pH above 11, then we can eliminate the precipitation. Next slide, please. So this is a detail of the bench test observation. Like I mentioned before, we made two different 5% CPS solutions. One is just potable water, the other one is pH adjust. So immediately we make these solutions, we find there's coarse suspended particles from the potable water 5%. And they are fine and suspended particles from pH adjusted 5%. And after 15 minutes, we find these coarse particles start to settle, but this fine particle from pH adjusted 5% CPS is still suspended. And after 24 hours, we find these coarse particles start to adhere to jar, but the fine particles did not adhere to jar. As I showed on the last slides, the difference of the two jars. Then finally, we filter both solutions through 100 micrometer filters. And we find these coarse particles are filtered out, so they are precipitated. They cannot pass through the filter. But these fine particles, they pass through the filters. That means they are not precipitated. So with this in mind, we know as long as we increase our pH, then we can eliminate the precipitation and hydrogen sulfide. Next one, please. So we apply this concept to a full-scale implementation. So first, when we purchase this 29% commercial CPS, we need to dilute to 5%. So we need a mixing tank. As you can see from the photos, those orange color, about 8,000 gallon closed top frac tanks, that's the mixing tank we use. The reason we use closed top is because we are making this chemical reductant. We don't want them to expose to air because that will oxidize the reductants. So the sequence is first we add water into the tank. Then we add alkaline, that is sodium hydroxide. Make sure the pH is above 11. And then we add some buffers. So the reason we add buffers is we want to make sure that after we inject this 5% CPS concentration into the aquifer, we know it will dilute again and the pH might drop. So that's why we add this buffer so that we can maintain high pH or slow down the pH changes. And finally, we add CPS. Make sure the total concentration, the pH is less than 11 and higher than 11. So this sequence is very important. We cannot mix them. For example, if we add water in the tank first, then we add a CPS, then immediately we'll see the precipitation. Then that's too late. Yeah. Then injection well, like I mentioned, we have 3 injection wells. And the well screen is from 155 to 175 feet below ground surface. Because 155 is the groundwater table, and we pick the 20 feet screen intervals for our injection. The reason is because based on our previous experience, the Chrome 6 is generally in the top 20 feet below ground table. So that's why we pick these well screens. And our flow rate is ranging from 19 to 25 GPM. As you can see, it's pretty steady. We didn't see a significant reduce of the injection flow rate. And for the injection volumes, we have about from 25,000 to 30 gallons per well. You might question, if we keep the same rate of inference, 25, why we will have different injection volumes? Yeah, this is because we adjust the injection volumes based on the sand portion along the well screen. Because usually when we inject the solution into the wells, the solution come out from the sand portion. So for example, if the sand portion is 80%, so we just inject 80% of the volume. That will help us to reach the required ROI. And we finish the injection in 4 days. Within a week, it's pretty quick. Next slide, please. So this is our layout of the CPS injection. As we can see, the side 1 is on the north of the road, and is currently an empty space. So that's why we put our mixing tank, our pumps, our chemical storage on side 1. And then after we mix the CPS solution, we pump over the road. As you can see, we have this tractor-rated crossover ramp to protect the pipes. And after CPS cross the road, it will get into the manifold, shown on the bottom of the photos. And from the manifold, this manifold is on the road side of side number 2, which is on the south side, and then injected into the 3 wells that's showing the 3 circles on the project site 2. Next, please. So this is to show our field observations during the injections. After we have this pH-adjusted CPS solutions, we don't see any calcium precipitations in the mixing tank, pumps, pipes, meters, etc. And this solution is very easy to deliver, so we didn't see any increase of the delivery pressure or the decrease of the flow rate. As we can see, it's ranging from 19 to 25 ZPM. And that also implies there's no precipitations in the injection well screen. But actually, after we inject the CPS, we did a video survey to look at the well screen, and we find there's no precipitations on the well screen. And the absence of the calcium precipitation also means we have more CPS available to treat Chrome 6. So that means we can have less chemical. It's a kind of a cost setting. And if we have no precipitations on the injection well screen, that also means we can reuse these injection wells next time. So that's green and sustainable. Because it's good to deliver the CPS solutions, so we have a radius of influence exceeding 20 feet. Next slide, please. So this is our Chrome 6 performance monitoring for CPS injection. We select 3 groundwater monitoring wells. All of them are within the 25 feet ROI of the injection wells, so that it's easier to observe the performance. So before the injections, all these 3 wells are all above 5 milligram per liter. So that's a threshold for bacteria to biodegrade the TCE. And after 1 month after injection, we find ND for all these wells, the ND of the Chrome 6. And 2 months after, we also find the pH return to neutral range, and dissolved oxygen DO less than 1 milligram per liter, and ORP, oxidation reduction potential, negative. So these are favorable conditions, environmental conditions for anaerobic biodegradation. So we start the combine the ISCR and EAB. And once we start this combined ISCR and the EAB, they will create reduced conditions that will maintain low Chrome 6 concentration and to prevent the rebound of Chrome 6. So 4 years, actually we did the quarterly monitoring, and after 4 years, we find all these 3 monitoring wells, the Chrome 6 still ND. So Christy will give a presentation of the ISCR and the EAB. Thanks.
Thanks, Jim, for summarizing the CPS injection work at Site 1 to treat those high concentrations of hexavalent chromium. Next, I'll take over presenting and talk about that remedy for Project Site 2. So the CPS injections performed were very successful at knocking down the hex chrome concentrations within the treatment area near the roadway, but there was still residual hex chrome present outside of that treatment area. Therefore, the combined ISCR and EAB remedy for Site 2 was intended to treat both hex chrome and TCE. When these 2 technologies are implemented together, a number of physical, chemical, and biological processes combine to create strong reducing conditions in situ that stimulate dechlorination of organic solvents and degrade other recalcitrant compounds like hexchrome. The natural state of the aquifer at the site was non-conducive to natural biodegradation. The aquifer was oxic, total organic carbon, methane, and ferrous iron values were low, and ethene and ethane were not previously detected, indicating natural attenuation of TCE was not occurring. Therefore, we injected amendments to induce aquifer conditions suitable for in-situ remediation. ISCR was implemented by injection of a reducing agent, ferrous lactate, to drive abiotic degradation by direct chemical reduction with reduced metals, while EAB was implemented by injection of organic substrate, electron donor in the form of emulsified vegetable oil, to serve as a carbon source to stimulate biological dechlorination of TCE. We also used a pH buffer to maintain neutral pH conditions, and a microbial culture was injected to ensure the right population of microbes was available for the complete dechlorination of TCE to the non-toxic end product ethene. The graphic here shows the biological reductive dechlorination pathway of TCE along the bottom with the yellow arrows. So along this pathway, the carbon-chlorine bond of the chemical are broken and a chloride ion is released, sequentially dechlorinating TCE to cis-TCE to vinyl chloride, and then to the non-toxic degradation product ethene, and finally ethane. But the primary abiotic degradation pathway is indicated by the gray arrows. For TCE, chloroacetylene is formed via dihaloelimination, leading to the formation of acetylene and then ethene. Acetylenes are energetically favorable to support microbial growth and are therefore used quickly once they're formed. As such, it's difficult to detect acetylenes in the field. Abiotic transformation pathways are often characterized as not having observable transformation products. You won't hear me talk about acetylenes again for that reason, and they're just hard to detect in the field. So the fieldwork for this project was performed late in the summer of 2017, about 4 months after the CPS injections. We installed 15 new injection wells for the remedy, with well screens up to 190 feet below ground surface. The photo here shows multiple drill rigs installing wells simultaneously at the site. Following a baseline sampling event, the injections were completed over a period of 14 working days. Flow rates during the injections varied from 0.2 up to 12.1 gallons per minute. And here you can see listed the tens of thousands of pounds of amendments that were injected. The selected organic substrate was Newman Zone by RNAS. It's a food-grade lactate and soybean oil emulsion product, which is a blend of fast and slow-release electron donors. Then ferrous lactate, which is a non-proprietary soluble food-grade iron product, was selected as the ISCR reagent. Neutral Zone by RNAS was the selected long-lasting pH buffer product used to maintain groundwater pH in the near neutral range. And finally, KB1 by Serum was used as the bioaugmentation culture. KB1 consists of a naturally occurring microbial culture that contains Dehalococoides, the only group of microorganisms documented to promote the complete dechlorination of chlorinated ethenes to non-toxic ethene. This image shows the injection well layout at the site. The 15 injection wells are shown as red dots. The groundwater treatment program was designed to treat groundwater in the TCE source area where the highest TCE concentrations were detected in groundwater. But the injection layout was constrained by the presence of the building to the south and the road to the north of the plume. The 15 injection wells were spaced approximately 40 to 50 feet on center in a staggered grid layout. A combination of radius of influences of 20 or 25 feet, the red or blue circles on the map respectively, were used for the proposed treatment area, and that radius of influence was used to determine the required injection volumes for each injection well. The outermost injection wells on the upgradient side of the treatment area, so the south side, were completed first, followed by the completion of injection wells down gradient and in the center of the treatment area. That approach reduced the potential for lateral migration of contaminated groundwater during the injections. This slide provides an overview of the field activities. The two images on the left show the ferrous lactate product, which is a powdered product. It was mixed with makeup water, the food grade soybean oil, and pH buffer in on-site mixing tanks, and then injected as one solution into the 15 wells. The middle two and top right photo show the mixing tanks and injection manifold setup. The photo on the bottom right shows the injection of the bioaugmentation culture, which was completed immediately following the injection of the other amendments. Since the completion of the injections, performance monitoring of the remedy has been completed quarterly for over 4 years. Let's start by looking at some geochemical and general chemistry results. The right aquifer properties are the key to any in situ remedy. The 3 wells in the table are shown by the yellow highlights on the map below. I've ordered them in distance from injection wells. LIW10 is an injection well. MW30 is about 10 feet from an injection well, and MW8 is about 18 feet from an injection well. As you can see from these baseline results from right before the ISCR and EAB injections, total organic carbon concentrations were low, ferrous iron concentrations were low, and ORP and dissolved oxygen were quite variable. So now the baseline data remains in the top table, and the bottom table shows the results following the injections. Total organic carbon and ferrous iron increased. ORP was consistently negative, and dissolved oxygen decreased to below 0.63 milligrams per liter at each of the wells. These parameters, along with others which I haven't shown here, such as near neutral pH, indicate that the injections were successful at inducing aquifer conditions conducive for TCE degradation. Okay, next up, to set the stage for the contaminant results, let's look at the dechlorinating bacteria results. Dehalococoides is known to degrade TCE to ethene through reductive dechlorination. So that's the bioremediation action that we're attempting to enhance with this remedy. The 3 wells within the treatment area, which were routinely analyzed for dehalococoides, are LIW10, an injection well, and then MW33 and NW34, which are 2 monitoring wells shown with the yellow highlights on the map. Both of these wells are at the edge of the radius of influence from the injection wells nearby. Generally, a dehalococoides concentration of 10,000 cells per milliliter is a good indicator of whether a site will have success with biological reductive dechlorination. As shown by the dehalococoides results on the table here, the microbial population proliferated near the injection well soon after injection, and results have generally varied from 1,000 cells per milliliter up to 1 million cells per milliliter. But you'll notice that it took almost 2 years for the dehalococoides microbial population to increase at MW33 and MW34. These wells are the furthest away from the injection wells. It's known that during injection, the microbes would get diluted further away from the injection wells. So it makes sense that it took some time for the microbial population to multiply to higher concentrations throughout the entire treatment area. We're not entirely sure if that's the only factor controlling these concentrations, or if perhaps it also had to do with the heterogeneous nature of the formation or variations in groundwater flow. But it's clear that at about 2 years after the injection, the dehalococoides population increased at MW33 and MW34. Over the last year and a half, the dehalococoides concentrations have fluctuated around 1,000 cells per milliliter at those 2 wells. This shows that the microbial population has been stable and has reached equilibrium across the treatment area. But remember that I said a dehalococoides concentration of 10,000 cells per milliliter is the gold standard for successful bioremediation? Well, as you can see, the results from MW33 and MW34 aren't quite at that level. So we've recently performed additional microbial analyses to provide another line of evidence that the correct microbial population is present at the site for successful bioremediation. So to confirm the potential for complete reductive dechlorination of TCE to ethene, DECHLORINATIN's functional genes, including TCEA reductase, BAV1 vinyl chloride reductase, and vinyl chloride reductase, were also analyzed during the first 2 quarters of 2021. The TCEA gene encodes the enzyme responsible for reductive dechlorination of TCE to cis DCE in some strains of DECHLORINATIN. The presence of TCEA gene provides additional evidence indicating the potential for dechlorination of TCE. And when either of the vinyl chloride reductase genes are detected, complete reductive dechlorination may still occur even with moderate DECHLORINATIN concentrations in the range of 10 to 10,000 cells per milliliter. So as shown by the results in this table as of May 2021, the presence of TCEA and vinyl chloride reductase genes, along with those moderate concentrations of DECHLORINATIN, indicate that the appropriate microbial populations are present in the treatment area to fully dechlorinate TCE to ethene. So the functional genes provided another line of evidence that the aquifer is primed for bioremediation. So that all leads us to the most important data, the contaminant concentrations over time. The next few slides are going to summarize hexchrome and TCE concentrations over time at a few select wells. This chart shows LIW10, an injection well near the northwestern end of the treatment area. Prior to the ISCR and EAB injections, hexchrome was above 10,000 micrograms per liter, which is above that inhibitory level for TCE degradation. And TCE was at about 1,000 micrograms per liter. Immediately following the injections, hexchrome was reduced to non-detectable levels, and TCE concentrations declined. 1 year after the injections, TCE has decreased to below 1 microgram per liter, and concentrations of both contaminants have remained very low for 3 years now. Take note of the background TCE concentration shown here at 100 micrograms per liter. The remedial goal at this site is not necessarily to achieve the maximum contaminant level of 5 micrograms per liter, as there are upgradient TCE sources as well. The remedial goal was to reduce the mass of TCE in the source area to the extent practicable and minimize further migration of the TCE groundwater plume. At this location, TCE has been reduced to well below background concentrations. Now let's look at the results for MW30, which is about 10 feet from one of our injection wells. At this location, hexchrome concentrations remained high prior to the ISCR and EAB injections, but by the 3rd sampling round after our injections, the hexchrome concentration had dropped to very low levels and then have remained low. After the hexchrome concentrations dropped below the inhibitory threshold, TCE degradation accelerated and has remained well below the background TCE concentration for over 3 years. At well MW8, the hexchrome concentration dropped significantly to about 100 micrograms per liter following the CPS injection, and then was polished off to non-detect after the ISCR and EAB injections. However, the TCE concentrations didn't significantly change until almost 2 years after the injections. This monitoring well is located near the edge of the injection well radius of influence, and as we learned earlier from the DECHLORINATIN results, it likely took the microbes almost 2 years to proliferate to significant concentrations at that edge of the radius of influence. So here, at about 2 years in, TCE concentration from over 200 micrograms per liter to close to 10 micrograms per liter. And the TCE concentrations have remained below the background concentrations for over 2 years now. So it seems that about 2 years in switch occurred and the DECHLORINATIN bacterial population was able to take over and start doing its work. This chart shows TCE and dechlorination products, cis-DCE and vinyl chloride for well LIW10 over time. Prior to injections, TCE was at about 1,000 micrograms per liter, cis-DCE was at 10 micrograms per liter, and vinyl chloride was not detected. After the injections, TCE concentrations declined, but there were spikes in cis-DCE and vinyl chloride as the reductive dechlorination process proceeded, which is expected. Eventually, cis-DCE and vinyl chloride were also dechlorinated by ongoing bioremediation, and over the last year, results for all of the chlorinated contaminants have been below 1 microgram per liter. Okay, so in conclusion, the commingled hexavalent chromium and TCE plume required a unique combined remedy approach. The remedy had to overcome hexchrome's inhibitory effect on TCE biodegradation while also preventing unacceptable secondary impacts to soil permeability and groundwater geochemistry. CPS is a very fast and effective way to reduce hexchrome concentrations, but in typical applications, it has a lot of negative impacts on soil permeability and aquifer chemistry, which would have had negative impacts on the TCE remedy. Therefore, our initial work focused on developing a pH-adjusted CPS solution to treat hexchrome without all those negative side effects. Our bench testing determined that a CPS solution adjusted to a pH greater than 11 was the optimal CPS solution. During the field scale application, the pH-adjusted CPS solution showed good stability. There wasn't calcium precipitation in the above ground equipment and or the well screen. Hexchrome concentrations decreased drastically in 1 month, and rebound has not been observed over a period of 4 years. And the pH-adjusted CPS solution eliminated the common negative impacts during injection and provided favorable environmental conditions for the follow-on ISCR and EAB remedy. The next phase of the remedy was combined ISCR and EAB injections to simultaneously treat the residual hexchrome along with TCE. 4 years after the ISCR EAB injection, the hexchrome and TCE plumes continue to shrink and rebound has not occurred. In addition, geochemistry continues to remain in the pH neutral anoxic range, conducive to biotic and abiotic degradation. The microbial population is sufficient and stable, and no substrate refreshes have been required. Overall, the pH-adjusted CPS approach allowed the full remedy to be completed in a shorter time frame, and the combined remedy has been successful. And with that, we will take your questions at this point.
Thanks, Kirsty and Jim. That was a great presentation. If anybody has a question, you can feel free to put it in the chat box, or you can raise your hand using the raise your hand feature, and we'll call on you. So I see Mahir Chokshi. You can go ahead and ask for a question. You can unmute yourself.
Hey, Kirsty, Jim, great presentation. One question, if you go back to your conclusions, is this, and I might be using wrong words, but is this chromium fixation a permanent solution, or is it eventually going to need a polishing treatment? That's the first part of the question. Second part is no rebound 4 years. How long do you anticipate to have no rebound conditions, or at least the conditions of reducing concentrations?
The 4 years no rebound, that's because after the Chrome 6, after CPS injection, we have this combined ISCR and EAB. And this combined ISCR and EAB generate a reduced concentration, reduced conditions. Usually when the Chrome 6 under reduced conditions, it will be reduced to Chrome 3, the precipitate. So that's why we didn't see the rebounds for 4 years. And if there's no ISCR and the EAB, it will depend. Yeah, if we have sufficient and efficient treatment of Chrome 6, then there will be no rebound. Yeah, because everything will from Chrome 6 to Chrome 3 precipitate out. But sometimes if, like I mentioned, if there's a precipitation during the for the solutions, or your injection efficiency is not good, then maybe you will see a rebound in probably 6 months, and then you might need to add a second injection. And if we don't have any precipitations, if we use this high pH, then that means if we need to do the second injection, we still can use the same wells, because the well screen is not precipitate.
So Jim, if I might ask a follow-up. So I would say that the technical complexity is not in just pumping the chemicals in, but it's more about how it's designed and how it's implemented, right? That's where your team's expertise comes in.
Correct, yeah. Because the regular injection, they have this precipitation issue because they didn't adjust pH. Yeah, and we adjust pH, we make high pH, so we reduce or eliminate precipitation issues above the ground or during the injection or underground. Yeah. And again, we in addition to increase the pH, we also add buffers. Buffers help, yeah, to slow down the pH change after the injection into the aquifer.
We have a question from the chat, unless there's any follow-up on that one. So from Isabel Landano, she asked, how did you determine the radius of influence for the injection wells?
I can reply to that one regarding the ISCR EAB injection. So for that, we selected our, we had a design radius of influence that we were targeting of 20 or 25. We used that along with the lithology and the well screen to determine what volume of amendments the formation will accept. And then during the injections, we used a downhole probe at one of those monitoring wells at the edge of the radius of influence to monitor for pH and ORP changes during the injection activities to confirm that we did achieve that radius of influence.
For the CPS injections, once we know the ROI, relative influence, for example, we have 25 feet ROI. If we know ROI, pi r squared is the area that we need, and we times pi r squared times the screen interval, that is 20 feet of our, so that's the total volume we need. Of course, we need to times porosity. Yeah, for example, for sand is about 15%. So that's the relative influence area times well screen times the porosity. So let's come up with our volume of the CPS solution.
I see someone has their hand raised. Felicity Simpson from DTSC.
Hi, this is Felisha Simpson, DTSC. I have a question. Chrissy, I know you mentioned that it takes about 2 years for the microbes to kind of do their thing and help stabilize the reduction. And my question is there any way, I don't know, to cut that time in half? Are there any, technologies where they're, just out of curiosity, where the microbes, where they use, I don't know, different types of microbes, or maybe a combination of different kinds of microbes to, again, cut that time in half so that you see the stability quicker instead of the 2-year time frame?
Yeah, a great question. So one thing that could have been done, as I said, that the further away from that injection well, the lower the more diluted the microbial concentrations are immediately following injection. So one thing you could do would be install more injection wells and reduce your radius of influence. But that obviously is a cost limiter. We used the design recommended microbial volume from the vendor. And so next time, maybe we need to revisit those numbers some more. So perhaps injecting more could have helped a little bit, but I think a lot of it really is just based on the formation, the lithology, and the radius of influence.
Yeah, usually the rate of influence we have, that circle one is the theoretical. Yeah, the actual one is not circle. It might be a different shape. So that still depends on the actual site conditions. So maybe there's some areas or some location close to the injection well, but because the one water doesn't flow into that direction, something like that. So we might miss something. So that's why we try to do as much as we can to cover the whole impact area.
Okay, thank you.
Todd France, I see you have your hand raised.
Hi. So in discussion of CPS implementation with that hydrogen sulfide can be generated, which could be a safety issue. And I was wondering if during the field implementation, any of the CPS injections, if any hydrogen sulfide was detected from either the mixing equipment or the well heads or so.
No, during the injection, we didn't detect any hydrogen sulfide. According to that equation I shown on my slide, maybe that's because of we stopped the second chemical reaction, so that's why no precipitation and no hydrogen sulfide. So if you smell hydrogen sulfide, that means you also have some precipitations. So luckily, we don't have any hydrogen sulfide and precipitation.
Great, thank you.
Thank you.
I actually have a follow-up question on that. So if you did detect hydrogen sulfide, which would indicate also precipitation while you're in the field, what would you do to address that?
That's why we need to increase the pH in the very beginning. As I mentioned, during the dilution, the mixing, if you add in different sequence, then you will have precipitation, you will have hydrogen sulfide, then that will be too late. Either it will be difficult to inject and then you have to take care of everything. So the best way is we stop this from the very beginning. Yeah.
Right, that makes sense. Good design equals good outcome.
Right.
There's a question in the chat from Claudia. Do you expect the chromium to rebound when the donor is used up and redox conditions return to normal?
Probably not, because it's pretty stable. The chrom 6 precipitated into chrom 3 is very, very stable. Unless someday someone inject very strong oxidant, then story might change. But I doubt, just by nature, it won't happen. Yeah.
If there are any more questions, feel free to raise your hand or put your question in the chat box. We have about 2 minutes left. If there's any remaining questions.
All right, I'm going to jump in here, and if we guess we do have one more question here.
This is a question from Akshay Parenki. The natural matters in groundwater usually react with CPS and impact the CPS dose. How do you determine the CPS dose to treat chromium 6? Yeah,
so the CPS dosage requirement is site specific. So usually you have to do a bench scale treatability study to determine the dosage. And for this site, since we have so many successful previous experience. So we already know what's the CPS dosages from previous pilot test or full-scale implementation. So we just easy to take it from the previous documents.
All right, so I want to mention that the sign-up sheet for this presentation, if you're looking for CEU credits, is in the chat feature, or feel free to send me an email and I'll make sure we get that to you. Also wanted to take just a minute to talk about the next webinar that we're going to have, because it's a little bit special, a little bit unusual for us. We have a guest speaker, Dr. Isabel Cazarelli is a geochemist with the U.S. Geological Survey's water mission area. And she's been looking into the release of trace metals and arsenic from sediment into groundwater in aquifers that are affected by petroleum releases. What they found is that those changes in the geochemistry that are caused by the natural breakdown of petroleum hydrocarbons underground can actually promote the release and the mobilization of naturally occurring arsenic into groundwater. And so that geochemical impact can actually result in potentially significant arsenic concentrations in groundwater that could go on for years. So it's a pretty interesting topic, and we're fortunate to have her coming to our webinar series. That webinar is actually 3 weeks from today, September 29th, to accommodate her schedule. We're a little bit early on there compared to normal, but we will get an announcement out to everyone about this special webinar for Dr. Cazarelli. So you'll want to make sure that you mark your calendars, and hope we can all attend on that. With that, Jim and Christy, great presentation today. Really appreciate all the time and effort that went into that. Thank you to everybody else for joining us today. And with that, we'll close things down. Thanks, everyone.